welcome to Oddly Real. I'm Nem Stefanovic. The study of science is not only a way for us to explain our observable world, it's a way for us to understand the very foundation of our reality. Arguably, there's no bigger question than what is the origin of our universe? Perhaps one of the most bizarre ideas put forth is that of a Boltzmann brain. Boltzmann brains are rooted in the idea that if there's no limit to the amount of time that can pass, then even the most improbable event will eventually happen. Consider vacuum fluctuations in space that spontaneously produce particles that last for a brief moment in time and then annihilate. Or alternatively, think about random particles distributed in space which have random motions. It is possible that these particles could organize themselves into something coherent by pure chance. It is conceivable that these random particle creations or motions could produce something complex and functional, even a human brain. Now, if your first thought upon hearing this is that it sounds unbelievable and incredibly unlikely, then you'd be absolutely correct. However, recall that we said we're assuming that we had no time limit and that we could wait as long as necessary. We're not saying we can wait for centuries or millions or billions of years. We can wait unimaginably long, like orders of magnitude longer than the existence of the entire universe. In this situation, no matter how unlikely something is to occur, eventually it will occur. The implications of this are startling. In this scenario, there's a real chance that a disembodied brain, called a Boltzmann brain, could spontaneously come into existence, complete with memories of a fictitious past. But even stranger still, what if we are the product of such a brain, and what we think is our past and what we see as our universe is ultimately just an illusion? Is it possible that we're not really here, but a figment of the imagination of a disembodied brain that is floating around in a vastly empty universe? In order to understand Boltzmann brains and their implications for our reality, we first need to understand the concept of entropy. Entropy is a measure of possibilities for the arrangement of matter. At the subatomic level, matter can be arranged in many different ways, which we call microstates. The number of possible arrangements of these microstates to produce the observable matter that we see, or its macrostate, determines its entropy. Another way to think about this is to say that entropy is a measure of disorder. If the entropy is low, then there are only a few ways to arrange the microstates within matter. Fewer possible arrangements to produce what we see means it's a very well-organized, highly ordered system. Alternatively, a larger entropy means that there are many more ways to arrange the matter. The underlying microstates can be changed and rearranged in many more ways without visibly producing a difference in what we see. For example, if you carefully look inside a raw egg, you'll see a well-ordered structure that includes a yolk and surrounding egg white. The particles within the yolk are concentrated in the center of the egg, while the rest are distributed in the egg white surroundings. However, if the contents of the same egg are scrambled, the substance will take on more of a uniform structure. Those same particles that were clearly distinct in specific regions of the unscrambled raw egg are now found distributed throughout the scrambled egg in no apparent order. The particles are more disordered, meaning the scrambled egg has a higher entropy than before. But entropy is much more than just a measure of disorder. In fact, entropy is responsible for the direction of time itself. If we start with a raw egg and drop it on the floor, the egg will shatter and break apart. The egg goes from a well-ordered low entropy state into a disordered high entropy state. However, we don't ever observe a shattered egg spontaneously reconstructing itself. Similarly, a solid ice cube has more structure and order than a warm liquid glass of water. If an ice cube is added to a warm glass of water, the ice cube will melt. Again, we don't ever see a warm glass of water spontaneously heat up and produce ice cubes within. All of these observations are consistent with our universe evolving from a state of lower entropy into a state of higher entropy. We call this the second law of thermodynamics. We can determine the direction of the flow of time by noting how a system evolves from low entropy to higher entropy. But why does our universe move forward in time from low to high entropy? It's ultimately due to statistics. Simply speaking, the particles of a system have a greater probability to distribute themselves in a more varied range of microstates for larger entropies. When entropies are smaller and more organized, it's much more unlikely that the system will be in that state. There are fewer organized low entropy states than disordered high entropy states. If a system is left alone, it will naturally move towards a more varied disordered state. This is the driving force that makes all processes in the universe move forward in one direction in time. Strangely, though, there's a subtle problem with this explanation of the second law of thermodynamics. Let's take an example of an empty box that contains a vacuum. Let's introduce some air into one corner of the box. This is a low entropy starting state for this system of particles. When left alone, the air will naturally expand out into the box, occupying a larger volume with a wider range of random particle motions. The air went from a low entropy state into a higher entropy state as expected. But the motion of air molecules is random, so isn't it possible that by chance all of the air molecules could return to the one corner of the box where they started? The answer is actually yes. However, the chance of that happening is astronomically small. Yet it could happen, and that would mean that the second law of thermodynamics could be violated in that the system could evolve from a higher entropy state into a lower entropy state. In fact, there is a recurrence theorem that says that a system of particles that is confined to a bounded region, like our box, will eventually reset itself back to its starting state. It will not only do this once, but actually an infinite number of times. Given enough time, every possible state will occur and repeat over and over again forever. It's not just a chance that it will occur, but it is guaranteed to occur. By extension, this is also true for something like a warm glass of water that is left on a table. We could watch that glass of water over a lifetime, even over the lifetime of our universe, and never see any discernible change. Yet, if we wait for an indeterminate amount of time, many orders of magnitude beyond the lifetime of the universe, then at some point we would expect to see the warm glass of water heat up and generate ice cubes within, in opposition to the second law of thermodynamics. In the glass of water, for example, it might contain upwards of 10 to the power of 25 molecules of water, but it would take 10 to the power of 10 to the power of 25 years to see this happen. This is unfathomably long. So does this even matter to us, since the chance of violating the second law of thermodynamics in any meaningful way seems essentially negligible on the timescales of our universe? This does have an interesting implication for the origin of our universe. We call these kinds of unusual and improbable spontaneous arrangements of matter fluctuations from thermal equilibrium. As strange and improbable as it is, there is an incredibly small but non-zero chance that particles in random motion will spontaneously arrange themselves into something with structure given enough time. Since our universe is moving towards more and more disorganization, or increasing entropy, it stands to reason that one day the universe would have increased its entropy to its maximum limit. Any particles and energy left in the universe would all be randomized and well mixed such that the energy would be evenly distributed everywhere. In this situation, no more work could be done and the universe would essentially be dead without any activity. This is called a heat death to describe one possibility for the end of the universe. Yet, as we know, there are still going to be random thermal fluctuations for the particles within. If time has no limits, then even these random fluctuations could lead to collections of particles that result in something with structure, like the formation of a rock, or maybe a planet, or even a star. Wait long enough, and maybe a whole galaxy will come into existence, or perhaps an entire universe. The larger the resultant organized body, the longer one would have to wait to see it. It's exponentially more likely that a small particle would fluctuate into existence rather than an entire planet. This brings us to the Boltzmann Brains scenario. Instead of fluctuating a whole universe into existence that would produce living, intelligent beings within it, it's actually much more likely that a person with a brain and memories would fluctuate into existence directly. Even stranger still, it's even more likely that just a disembodied brain could be fluctuated into existence, such that it remembers being in a universe. If our universe was at its core infinitely vast, with no limits to time, and in a state of thermal equilibrium, then probabilistically, we are more likely to be disembodied brains that fluctuated into existence. We would be Boltzmann brains that think we are living in our well-ordered universe rather than the product of a real such universe. It's a very surreal thought. How do we know if we're real versus thoughts in a disembodied Boltzmann brain? There are some interesting arguments about the implications to being a Boltzmann brain. First of all, we know that when something comes into existence via a fluctuation, it's always far more likely that a smaller, minimal version of something would be created. For example, if you look around to see that you're on planet Earth, it's exponentially more likely that just the Earth and its immediate surroundings were created, rather than Earth and the entire universe. Even being inside of a house, it would be more likely that just the house was created, meaning that beyond the front door, there may not be any universe at all. Yet, we do know that technically it's still possible to fluctuate a whole universe if we wait long enough, so maybe that's not a completely convincing argument. What about the coherence of your memories or knowledge in your mind? That would also have to fluctuate into existence. That means that your understanding of logic and the consistency of your memories would all have to be perfectly aligned. Most times, a fluctuated being wouldn't have that consistency, and their memories and knowledge would be fragmented and illogical. We call this cognitive instability. Yet again, maybe we just need to wait long enough and a person with fully logical and intact memories could be created. One particularly interesting argument can be made about what we observe in our universe and what we'd expect to observe if it was created randomly. Imagine we were looking at a box containing a mixture of gas particles. Let's say we only focus on one corner of the box, and we notice that by chance, the particles there have unmixed and have separated into two distinct gases. We know that it's extremely unlikely for this to happen, so it's an extraordinary sight to see this in one corner. But the rest of the box is filled with this mixture of particles, and the box is much larger than what's contained in this little corner. Knowing this, what would we expect to see if we turned our attention to the other parts of the box? Would we expect the gas to be unmixed everywhere else? Well, obviously not, since the chance of that would be almost negligible. We'd expect that the gas would be well mixed everywhere else. We can extend this analogy to our universe. If we look at one part of it, perhaps in one direction out in deep space through a telescope, we'll see lots of order in stars, galaxies, and clouds of gas. If our universe randomly came into existence as a fluctuation, the probability is extremely high that much of the universe, if not all of it, would also be extremely randomized and disordered, much like our example of a box with gas in it. Yet, when we look at the other parts of our universe, we see the same order in the galaxies and stars there too. These galaxies and stars also obey the same rules and laws of physics wherever we look. These observations don't fit well with the idea that everything fluctuated into existence. There's another possible explanation for the existence of our universe that doesn't involve random fluctuations. Instead, our universe could be explained as having started from an initial point in time with extreme order and low entropy. The universe then evolved to have more disorder and higher entropy. In fact, this is exactly what we see today, where the second law of thermodynamics dictates the universe's continued evolution into more disorder. The consistency of our observations of every part of the universe shows a memory of those earlier ordered conditions of the past. This description of our universe where entropy was lower in the past is called the past hypothesis, and it fits much better with what we observe in the universe than the Boltzmann brain explanation. Why was entropy lower in the past? How did our universe come to be in that state in the first place? We just don't know, and that's an active area of research today. On that note, we'll end our discussion of Boltzmann brains and their implications for our universe. I hope you enjoyed this episode, and remember, oddly real, really interesting.